over to Yang for his second lecture.
Okay. So hello everyone, welcome back. Good morning. Okay. So let's continue with this introduction to computational algebraic geometry. So I hope that during past 2 days you had some chance to at least have a look of the section 1.1 of Robin Hartshorne's textbook Algebraic Geometry, and also try to type in some of my programs on the slides. So last time we talked about the important thing, this good generating set of an idea. So the good generating set is called Gruber basis. So I just show you that you can do this kind of elimination with the Gruber basis easily, for example, in Mathematica. Okay. And today I'm just go along in this direction to give you more applications of Gruber basis. Okay. So one thing I have to mention is this is a very important trick. This is the Zariski open set versus Zariski closed set. So in many cases, okay, we get some kind of constraint in physics. They are not some kind of equality, but this kind of inequality. So this kind of thing may think that, okay, that's bad. It's not Zariski closed, it's Zariski open. So we cannot use some algebraic geometry, this kind of idea of variety language to describe it. But don't worry about that. If you say some kind of inequality like this, you can also put it in the way, just like a closed set. So the trick to apply this kind of open set is you introduce one additional variable called W. Now you have x1, xn, W. And before using this trick, you have this equation, but then you can say this condition is equal to say you have this equation. Because if this f could be 0, then you have some kind of wrong identity 1 equals 0, that's impossible. So that means f cannot be 0. So you can say you can just put this kind of Zariski open set embedded in the high dimensional affine space as Zariski closed set. That's very important. That means if you have many kinds of polynomial equations and several constraints, and then you can put this kind of constraints like this to this kind of polynomial equations. Okay, so for example, if you have this kind of idea, okay, there's some kind of random idea I generated. Suppose that I don't want any solution with x equals 0. So in this case, I can put one auxiliary variable w, and I say w times x plus 1 equals 0. So x cannot be 0. And then I can just do everything I want. I just use this w as one additional variable and do this kind of computation. I can do everything, just trust me. Now you have this kind of equation, you can numerically solve it. So possibly, actually I tried, you get one solution with x equals 0. But then if you consider this kind of additional condition and also treat this w as a variable, then you find that actually you don't find any solution with x equals 0. It's impossible. So sometimes we also want to calculate the intersection of two ideals. So you can see from algebraic geometry, if you take the union of two varieties, then it's equal to say I have the intersection of two ideals, and then I try to find the common solution. So in many cases, okay, you have two geometric objects. You want, okay, the union of them, and then you want to find the equation system which defines the union. That's an easy question in algebraic geometry. So the thing you can do it is, okay, you just need to find the intersection of these two ideals. That's also an idea. So there's one very trivial algorithm to do this. So you have x1 to xn, but then you introduce a parameter t here, and then you consider t also as a variable. Now you consider this kind of generating set. For all generators from I1, you multiply by t. For the other idea, just say take the generating set multiplied by 1 minus t, Now you have the variables x1 to xn and also t in this bigger ring here. But then you do this kind of intersection. You do this kind of intersection is equal to say I try to eliminate the t variable in this bigger ring. And then if you can eliminate the t, then what still left? That is generating polynomials for the intersection I1 and I2. So here, that's an example. Now I have, in the beginning, I have 3 variables. And here, the first idea defines one circle. There's another circle here. But these 2 circles in the 3-dimensional space that's orthogonal to each other. So suppose I'm interested in the union of the 2 circles. It looks a complicated geometric object, but I still want an algebraic description of it. That can be easily done. You just use what I said, this kind of t and 1 minus t language, and try to get rid of this t here. You get this idea in x, y, and z. So if you really try to solve this idea, and then you get 2 circles. This is the intersection of 2 ideas. Okay.
Sorry to interrupt. Carlos has a question.
Yes, I have a question. I'm not very good at reading weight matrices. Are you doing like a lexicographic for T and everyone else? Degree reverse in that weight matrix to do elimination?
Yeah, so here I use the block ordering. So this one means I use a lexicographic for X. This one is the lexicographic for T. This one is a degree reverse lexicographic for all the other variables.
Okay, thanks.
Okay, so I guess this one describes the union of 2 circles. That's a simple question, but the thing is here it's not so efficient because you will say that you introduce this new variable t and you multiply this t for all the generators. You increase the degree of the polynomial. Then you get some quite heavy computation. So I think in the last lecture, I will introduce some better algorithm for doing this. Okay, so let's talk about the real world computation. So all the previous computations, I put it in Mathematica notebook. I will upload it to Slack. The thing is, this kind of computations are very trivial, very fast, less than 1 minute. But in the real world, it has some hard computations. On one hand, my mathematician friend told me that if you can really get the global basis of an idea, then you can do everything with the idea. Okay, but if you can't calculate the global basis of the idea, then although you have this very nice formalism of our algebraic geometry, but really you couldn't do much with that. However, the global basis computation is usually quite heavy for research problems. And for many cases, you need some kind of external professional programs to do that. So one thing you can try is definitely Maple. So Maple has some very advanced algorithm for the computing global basis. Another professional program is called Singular. So Singular is a specific program for the computation of algebraic geometry. You can also try this Macaulay 2. Okay, both Singular and Macaulay 2 are freeware. You can also try this Magma. Magma is highly efficient, but unfortunately, it's not free. You have to buy the license to use it. There's also some small package called FGP to do this fast new algorithm computation of the global basis. So today I'm going to introduce this freeware because this one is quite easy to use and is free. And the good thing is actually you can call Singular in Mathematica. So I will tell you that there's a, so here there's an interface called singular.m. So this is a website where you can really download it. So here you can say, if you can really install this package, this singular.m, then you can call a lot of singular commands inside Mathematica. But one thing you have to be sure is first, of course, you have to install Singular. Okay, install Singular. And I have to say, it's quite difficult to install Singular on Windows, but it's quite easy to do that on Mac or Linux. And also, this one is a nice package, but somehow you have to by hand modify the singular.m try to edit the path to find where the binary location of the singular program. So that's tricky. You have to change this package a little bit for your computer. So if it's really installed, then you have several commands you can run. The first one is a singular std, that is to calculate the group basis in singular with Book algorithm. The other one is a singular slim GB, that is to calculate singular still with the Book algorithm, but with a better strategy to find the ordering which S pair to be reduced first. This one is called a singular normal form, singular NF. So this one is somehow equivalent to this polynomial reduce in Mathematica. But the last one is actually quite useful because in many cases, it's much faster than the polynomial reduce in Mathematica. Then you may try to use this singular NF for the computation. I have to say one thing. So frequently you have some kind of a large scale linear system to solve, especially it could have several parameters. So if you don't know some other kinds of advanced methods, okay, but I'm sure you will because you are also studying this kind of finite field methods from Ben Page's class. But anyway, if you don't know some advanced method, it's just call this singular slim GB to do Gaussian elimination. The reason is if all the equations are linear, then to calculate the group basis is just equivalent to say, I calculate the Gaussian elimination of the matrix. But this one is much faster than the row reduce in Mathematica in many cases. So these three commands you can use for the first step of using singulars. Everything you can just do it in Mathematica. Okay, so I just show you one example. This is again some kind of trivial example. There's something called Cyclic 6 ideas, kinds of simple idea people use for the benchmark. I changed this idea a little bit. So previously there's some kind of constant one here, but I changed it to some parameter C and D. So the thing is actually still a simple computation for group basis. Now you have the variables X, Y, Z, T, U, V here. So if you do it with group basis Mathematica, you do it with the best monomial ordering degree reverse lexicographic, and then you claim that the C and D, they are parameters. That computation is still quite fast, but still takes 3 minutes or something. But then you can compare with the singular STD. So the singular STD actually is doing almost the same thing. Okay, the same idea, the same variable list, same ordering. But in this singular STD, actually you don't need to claim C and D. They are parameters. They will detect some kind of undeclared variables and just automatically treat them as parameters. Now you can see it's much faster. Okay, not dramatically faster, but quite fast. So the thing is, the interface is quite convenient to use in Mathematica, but the bad thing is it will write the input file on the disk and call singular to write and ask singular to get the output file on the disk and read from Mathematica. So of course it's not very efficient. So in the future you will find some better way to do it. For example, to compile to MathLink or something like that. And also there's some kind of overhead for this interface because this kind of namespace of Mathematica and singular quite different. So in many cases you have to rename all your variables to run it in a singular. So this package will do this kind of rename of variable automatically for you. But this one is also a slow step. Okay, but right now for if you try to just to learn computational algebraic geometry and also try to do the project, this interface is enough. Okay, so I give you some kind of quite funny problem. So actually you can use the globular basis to solve this kind of puzzle called Sudoku. I'm sure most of you have played Sudoku for a while. That means, okay, you have this kind of 9 times 9 table. You have some numbers inside that. You want inside each small 3 by 3 box, you have the distinct number 1 to 9, and also for each horizontal line, and also for each vertical line, it has a distinct numbers 1 to 9. Okay, that's a constraint on that. So you may try to spend some time to solve this puzzle and find some kind of algorithm, but actually this one can be worked out by brute force with grouped basis. So in the beginning, you don't think that it's a polynomial question. There's no polynomial. I just want to distinct the numbers where the polynomial is. So I try to invent some kind of polynomial-like constraints for the system. So for this xij, okay, that's the coordinate x is I and j. So for each xij, as I say, of course, it's xij should satisfy this f xij equals 0 because this x could either be 1 or 2 to 9, just as 9 different choices. So that's kind of a trivial polynomial constraint. The other thing is less trivial. So if you want, so for example, okay, for this kind of small boxes like this one, this x11, this x12, these two numbers cannot be the same. They cannot be the same. It seems as not a Zariski closed set. It's not some kind of ideal problem, but actually that is. So the trick is now you have this x11, this x12, these two small boxes. These two numbers cannot be the same. So you know, okay, this capital F, this capital F x11 equals 0, capital F x12 is 0. But then you can take the difference and divide by x11 minus x12. So why could I divide by that? So the thing is you already required this x1 cannot be x12. So this denominator cannot be 0. So it's legal to divide by that one. So if you divide by that one, you know, okay, these two polynomials are 0 and the denominator is non-zero. So this new polynomial in x11 and x12, that must be 0. So you again, you convert some kind of Zariski open set to Zariski closed set. So that's a quite a tricky way to put this kind of constraints to some kind of polynomial equations. Then of course you get a huge number of equations because for each empty box you need some variable here, okay? And also you need to put all these kind of constraints. So instantly you get 800 something equations, and note that they are not linear equations. Okay, this is degree 9, and this is some degree 8 equations. Okay, so the thing is, okay, with so many equations, do you think I can really solve it? Actually, it's possible. Okay, it's possible to solve it, as long as it's not a very difficult Sudoku problem. So there are many tricks to do it. The first trick you need to apply is just what Ben mentioned. You have to use a finite field instead of rational number. So here you want to use z over p, and you can treat as p some prime number larger than 9. It could be 11, it could be 13, whatever number you like. The thing here is if you work with rational number of integers, it's getting slower and slower for global-based computation. But with a finite field, it's possible to finish it. And here you only have 9 choices. Okay, it doesn't matter if you are really using this kind of rational number or using finite field. Okay, this equivalent good. So for this simple, actually it's quite a simple Sudoku problem. You put this, okay, 800 something equations, okay, in many variables, and then you put it as some kind of generating system of one idea, and then you can ask a singular to calculate global basis. So global basis have good properties. If you know that kind of equation system has only one solution, then immediately, okay, if you really get the global basis, then you find that all the results would be just some linear generators. And all the linear generators are just one variable equals a number. So here, if you use the singular and also singular interface for that group basis, although the 900 equations and the degree at most 9, it seems like impossible to solve, but actually this one can be solved because just do the group basis. Within 5 seconds, the singular can calculate the group basis and find x11. minus 1 is 0, so x11 is 1, x12 minus 3 equals 0, so this is 3, okay. So that just means in the beginning, this system is good. It contains all the constraints, but the degree is very, very high, degree 9, and there are so many equations. But after you clean up the generating system, getting group basis, then you get arrays, all linear, then only one solution and solve this stupid problem, 5 seconds. But you may argue that it's not fast. Because if you have some kind of traditional algorithm, like a backtracing algorithm, like you solve it maybe less than 1 second, very, very fast to do this kind of computation. But a good thing is, okay, if somehow this sudoku problem is not well defined, for example, has 2 solutions, okay, then if you really run this kind of backtracing algorithm, it takes quite a long time to go through all these kind of situations. But the group basis, if you say if this one is a ill-defined sudoku problem, and then you try to calculate the group basis, then you will not going to get all linear equations. You get most of them are linear equations, but one of them is a quadratic equation. So that means somehow it has some kind of ambiguity in the solution. You have 2 solutions. So group basis in this way can also solve the ill-defined sudoku problem and find the total number of solutions. That's something new for this kind of computation. Okay, still you could have more complicated group basis computation. So you need some more advanced techniques in singular or in whatever program. So of course, I have to mention that the finite field is very, very important, not just important for matrix linear algebra. It's also very important for algebra geometry. So if you can do this kind of Gaussian elimination with finite field, then of course you can imagine that you can also do this kind of finite field fitting method for group basis. So there's already one library called this modular std mod std in singular. You just load this library and do it, and then it will do everything in parallel automatically for you. Calculate the group basis with different primes. You don't need to worry about anything. So after it's finished, it will convert the results from different prime numbers automatically back by Chinese reminder theorem and the lifting method back to rational numbers. Everything is automatic. This is quite convenient. But again, in singular, no matter you do it STD or this kind of slim GB or MOD STD, they are all somehow based on book algorithm. So fundamentally, it's not a very fast algorithm. Okay, you can get it better with parallelization, but still it's not something the best. So far, the best algorithm be some kind of a combination of F4 and F5 algorithm for group basis computation. This kind of algorithm, okay, I don't think that this algorithm, these original papers are so difficult to read. But the problem is, even you understand the original paper of F4 and F5 algorithm, if you try to write your own program to get something efficient, that's almost impossible. Okay, you need a lot of experience with programming. So fortunately, there's several good implements of F4 and F5 algorithm for group basis computation. One thing quite easily accessible would be the MGB. That is F4 algorithm implements in Maple for group basis computation. Or you can try this Magma program with very, very good, maybe fastest implements of F4 algorithm for group basis. And then you can definitely see some benchmarks comparing with the modern algorithm, F4, F5 algorithm versus book algorithm. So for many examples, you can say it could be 2 order of magnitudes faster than book algorithm. So for real research problem, possibly you would try some other tools, not Mathematica, even not a singular, some more advanced method for group basis computation. Okay. So it's a time for this second lecture. So second lecture would be some special case of the ideas. So first I will talk about how to decompose the idea to the primary ideas. And then I will talk about the special case zero-dimensional idea, which means the solution set of one idea. That's just a finite point set. So first, again, we talk about the this translation between the ideal and the algebraic set. So we already used this relation for many, many times. But then if you check the Hartshorne, there's another relation. So if you have this kind of union of two algebraic set, and then you take the idea of it, then basically what you have is the intersection of the two ideas. The proof is from Hartshorne's textbook. So here, okay, we said that the basic thing of the classical algebraic geometry is a relation between algebraic set and idea. And I said that it's very important that you, using Zariski topology, try to decompose one algebraic set or Zariski closed set into the union of several Zariski set until you find that okay, there's no way to go further. Then you get an irreducible algebraic set called variety. But in this is a geometric picture. Okay, if you have something higher than 2 dimensions, basically you can't do it by yourself. Then we need some algebraic way to do this kind of Zariski's topology decomposition of closed set. Okay, so you say if you find that okay, I have one Zariski closed set which is the union of 2 closed ones. From the algebra side, I find that actually it's one idea which is the intersection of 2 ideas. So that means we have to find a way given an idea, try to decompose that as the intersection of several ideas. So first I give you some definition. There's some kind of very basic things from commutative algebra. So that is first the prime idea. So the idea in a ring R is a prime idea. If you say if A multiply B is in this kind of idea, then that means either A is in this idea or B is in this idea. So this one is just like generalization of the prime number. Okay, so just remember that in number theory. Okay, so if you find that your 2 numbers A times B, okay, is divided by some prime number, then either A is divided by this prime number, or B is divided by this prime number. Okay. But then there's some kind of larger set than this kind of prime idea. It's called primary idea. So primary idea means if you have this A, B, okay, inside this I, then either A is in this I or B, okay, to some positive power is in this kind of idea. So it's somehow a generalization of the prime idea. So soon you will find that a prime idea must be a primary idea because n equals 1 here. On the other hand, okay, if this I is a primary idea, then if you take the radical of it, then this radical must be a prime idea. So then you check Hartshorne, you find that if I is a prime idea, then the solution set is irreducible. Or on the other hand, if some set geometrically is irreducible, then its idea is prime. So basically, there's a one-to-one correspondence between prime idea and variety. So here, this is a fundamental theorem for this kind of classical algebraic geometry, the Lasker theorem. So for any idea in a polynomial ring that has a primary decomposition, that means I can be decomposed as the intersection of several primary ideas. There's some kind of details here that you can read by yourself. Basic thing is this kind of primary decomposition is not unique. Okay, you could get different primary decompositions, but if you take the radical of this kind of primary idea, get prime idea. Okay, this kind of radicals, the prime ideas, they are unique. That's very important. So what's the geometrical meaning of it? You have one idea. Maybe it's quite complicated. Okay, but don't worry about it. Try this kind of primary decomposition. So geometry means maybe from this I to Y, you take the solution set. The geometric graph is complicated. But then you can say that if you have one decomposition on the algebraic side, but then if you change it to the geometric side, you see this I1, the solution set is Y1, and Y1 is reducible, and this I1 is primary. Then you can see from the Zariski topology, you decompose a very complicated algebra set to the irreducible varieties. So primary decomposition can also be done in Mathematica, of course, with a singular interface. So I have this kind of idea, of course, it looks quite trivial because you can say the second polynomial is factorizable. You have z plus y multiplied z minus y equals 0. So if you try to draw the picture of this, you'd better consider that this one has actually 2 components instead of 1 component. But you don't need to really draw the picture. You just use something called a singular primary decomposition, GTZ, this idea in several variables, then you get it. So the first one, okay, the first one is this is the I1, the first primary idea. So this is the second primary idea, but the singular also calculates the radical of it. So basically remove the multiplicity in this kind of idea. Then I can say that, okay, this one looks complicated by decomposing 2 elliptic curves. I have to say that primary decomposition is also quite a heavy computation. So still, okay, I think right now it's not as advanced as the development of new global basis algorithms. Still, people are using some classical algorithm called GTZ algorithm. I'm not quite sure in the future will be more efficient algorithm. And also, again, I have to say that, so here it's very, very important that to mention that this primary decomposition, the result depends on the fields you are using. Actually, for global basis computation, it's not sensitive to the field you are using, but this one is. Because if you put a plus here, then you have to tell computer you want to do it with Q or with this kind of QI or some kind of algebraic closure of Q, try to do the decomposition. The result will be completely different. But if you don't say anything about that, it will do the primary decomposition in Q, and sometimes you will get a surprising result. Okay, so I just want to show you quite interesting application in scattered amplitudes. So this kind of things are very similar to the on-shell diagrams. So there's one classical paper by Kosovo and long time ago about this kind of decomposition of the solution set of the maximum cut for massless two-loop double box.
Gabriele has a question.
Okay.
Sorry to interrupt, Yang. Can we go back a second to the previous slide?
Yes.
Even one more, sorry, the definition of the ideal.
Mm-hmm.
So, I mean, if we are on the complex number, so if I understood correctly, like a primary idea will be simply to have just degree 1 polynomials. Like, I don't know, if AB is in the ideal and AB are in R, then I must be in I and B must be in I. But I mean, since AB is a polynomial and I can factorize any polynomial.
Yes, you're right. Yeah, you are talking about if you take this ring to be CX and there's only 1X and everything is simple, then so just say that this kind of prime ideas, the irreducible polynomials. Or what are the irreducible polynomials? Then it's just the degree 1 polynomials. Yes, like that. Yes.
Okay.
Right. Yeah,
Sorry,
great.
I have very little experience with like a multivariate polynomial and their irreducibilities.
For this kind of multivariant cases are different because you say if you have this C, X, Y, but then you can take a circle, X squared plus Y squared minus 1. Okay, so this one, okay, is an irreducible polynomial. I can prove this one give you a prime idea. Okay, but this one not a point, and this is not degree 1.
Okay, thank you. So we have multivariate, we have a whole plethora of like complicated figures which are irreducible.
Yes.
Okay, thank you.
Yes. That just means if you basically geometrically, if you have the prime idea, just means the solution set, okay, from a Zariski topology is irreducible. It cannot be decomposed to some kind of simpler solution sets. Okay, so let's back to this classical paper. So Cosworth and Larson, long time ago, proved that if you consider the maximum cut in 4D for the method double box diagram, you have 6 solutions, and 6 solutions have a very nice feature, just like the on-shell diagrams. You can say, okay, for each 3 vertex, you can consider the helicity. Then you have this kind of plus and minus configuration. It has some graphic rules, and then you can easily classify that with 6 solutions. Okay, but from algebraic geometry, you can also get it from a different viewpoint. So the way to do it is just to say, I have 7 propagators for the method double box diagram, and then I have maximum cut. That means I put all the propagators equal 0. So I have 7 equations. And then I have for this L1, I have 4 variables in 4D, L2, 4 variables in 4D. So that'd be 8 variables and 7 equations. Okay. But then if you ask, but then you could say, okay, it seems like quite a complicated idea, but then you can do a primary decomposition. So singular can do it in just in 1 second to find that there should be 6 solutions. And these 6 solutions cannot be decomposed or simplified further. So this is the algebraic geometry way to decompose the solution set to smaller set. So also from practical viewpoint, it's important. So why? Because the thing is, in the next step, you may want to parameterize the solution if it's possible. But suppose you don't do this kind of primary decomposition, then you get in trouble, because if you really can parameterize it, that means there's a variety. First, it's reducible and it's irrational. But if it's already reducible, then there's no way you can parameterize it. There's no global way to parameterize all the 6 solutions. But then, if you do the primary decomposition into the 6 solutions, then you can find some way to rationalize it. Okay. I also have to go through some more mathematical concepts. That's called quotient ring. So some other way to think of the idea. So the thing is, you have this total set of all polynomials R, and you have an idea I here. So here we can have this equivalent class. If F is equal to G, that means the difference is in this kind of idea. So we use this kind of square bracket for the equivalent class. And then for the whole set of the equivalent class is called the quotient ring R over I. So this one is again, it's a ring. Okay, it's a ring. But then sometimes we use the viewpoint of the idea. Sometimes we use the viewpoint from the algebra set of the geometrical viewpoint. But sometimes use the quotient ring. So in the quotient ring, okay, actually you can check some algebraic book. If this I is a prime idea, then this quotient ring is a domain. Okay, there's no non-trivial 0 in this quotient ring. You can say if A and B is in this kind of quotient ring, then if A, B equals 0, that means A is 0 or B equals 0. Also, if I is a maximum idea, so maximum idea means I is the idea of R, and you can't find some bigger non-trivial idea between this I and R. Okay, so it's called maximum idea. So if I is a maximum idea, then R divided by I is a field. Okay, so that's some kind of basic thing from algebra. So before the break, so I quickly give you a very, very interesting example. Also, it's quite a deep example. Yeah. So actually, possibly you don't understand all the details, but just I give you some ideas of what's the usage of primary decomposition, what's the usage of prime idea, what's the usage of quotient ring. So this is the brute force computation of the Galois group. So you must have heard that if you have some kind of degree 5 polynomial equation, then in most cases you are not going to find the analytic solution by the radicals. Okay. All this is Galois theory. You see, if the Galois group of this polynomial equation is not solvable, then you are not going to find a radical solution of it. But the thing is, if you really have some kind of polynomial generalizes with particular form, this kind of coefficients, it's not so easy to get the Galois group. Okay, so, but with this kind of primary decomposition, prime ideas, okay, there's a brute force way to really get the Galois group. So to get the Galois group, how do I do this? So I explicitly construct the splitting field of F. Okay, so it's not easy. I don't mean I try to numerically solve it and then I get some field. That's wrong. I do everything analytically. Okay, there's no floating number. There's no error. Everything is exact. Now I just introduce x1 to x5 to be the 5 distinct roots of F. Okay, so I didn't say this one has a value. Okay, it's just some kind of symbols here. Again, I use this trick. Each this fxi should be 0. Okay, should be a root, and also this should be distinct, just like a Sudoku case. So this one gives you one idea, and I'm sorry, it's a type. This is now q over I. So this should be q bracket x1 to x5 divided by I. So this polynomial ring over I will give you a quotient ring. And it seems that you introduce this kind of symbols x1 to x5 into this kind of equations. It seems like a splitting field. But this I, it may not be prime. It may not be maximum. So this quotient ring is not a field. So it's not a splitting field. So how could you make it bigger? So to make it bigger, you consider the primary decomposition. Then take this I, then you take the primary decomposition. You find I1 to In here. You find several of them. So this I actually, for example, is I1 or this kind of radical I1 is bigger than I. Then of course, it's bigger than that. And this one is a prime idea. You can further prove that it's not just a prime idea. Okay, it's a maximum idea, because this one corresponds to a 0-dimensional algebraic set. That means if you really numerically solve this one, okay, just brute force numerically solve it, you get a finite number of solutions. So if you have one idea which is prime, and also have a finite number of solutions, it must be maximum. But since we are using Q here, it's not guaranteed that it's completely factorized. So it may not be, okay, just one point, actually have many points. Then the splitting field is this polynomial ring over this radical I1 here. So everything is calculable. Now you have this kind of polynomial ring here. Now I define this kind of auxiliary relation for all the roots different. I have this kind of idea. I have some group basis, that's simple. The hard part is to do this primary decomposition in singular of this Mathematica. This one takes a while to finish, it takes almost 1 minute to finish. But after finish, they get this kind of relations between different roots. Some of the relations are completely trivial. This like this kind of symmetric polynomial different roots would be a analytic rational number. Okay, that's a trivial. That's just the very simple permutation of roots. Okay, but that one is a non-trivial relation. That's some kind of very deep, very hidden relation about roots. All the roots are irrational numbers, but you have this kind of hidden relation. So if you don't have this kind of hidden relation between the roots, then no doubt the Galois group will be S5. You are not going to find an analytic radical solution. But since there's some hidden relation like this is exactly the solution. I don't mean I numerically solve it, and I by some kind of high precision numerics I find the relation. Just done by a group basis. So with this one, okay, the Galois group, we have a symmetry breaking from S5 to some subgroup of this Galois group. Okay, so how do we really find the Galois group? It's very, very easy. So you can find that I have this kind of actually, so the polynomial ring divided by this prime idea gives a splitting field. Now, suppose I say I want to really find the Galois group. That means I find all the permutation which does not change this idea. So I already said that, okay, if you want to find that after one permutation, if the ideas change or not, that can be done by group basis. This is the idea identification problem. So brute force, I consider 5 factorial permutations and put it into this kind of idea. I find that 10 survived, 10 survived. So instead I get S5, this Galois group should have the order only 10. And if you check the finite group table, you find that the only size 10 subgroup of S5 is D5. And then this one is the solvable group. So that means this one, although this one is a degree 5 polynomial, the solution can be analytically solved by the radicals because this is symmetry breaking. So this example just shows that it's primary decomposition, primary idea. This kind of concepts are quite useful for brute force computation. Okay, so I think we should have a 5 minutes break. I will come back in 5 minutes. And also you can type in some kind of questions, problems. Thanks. Okay. In 5 minutes, come back. I think during the break, I saw some of the questions. Okay, I think it's a very good idea to immediately after lecture. So after the lecture to upload the slides to the slide. I think this time it's important. I will upload this this mathematical notebook, although they are all trivial computations, okay, to slides. So you don't need to really type the program by yourself, you can just run it. But I ask all the students, okay, so be careful. Some of the computation cannot be done with Mathematica itself. You have to install Singular and somehow, and install the interface correctly, and then run this kind of advanced commands with algebraic geometry. Okay, so I hope you didn't get lost with the primary decomposition. I don't think it's simple because if you are okay, mathematical students, possibly you need like half of the semester to learn all these kind of things, this idea, primary decomposition, all these kind of things. Also, you need some time trying to understand what global basis is. Okay, but if you are really getting a little bit lost with the primary decomposition, it's okay because I think at least for my project, I didn't use this kind of advanced primary decomposition. But my project used this zero-dimensional idea because it's actually very basic, very simple thing. I think everyone can understand. So we talk about the situation. We have one idea, and the algebraic set, the solution set is zero-dimensional. That means a finite number of points. So this one is also quite a common case in physics. For example, if you solve the CHY scattering equation, then of course you have something like this. If you solve the beta ansatz equation, okay, in the correct way, you also get a finite number of solutions. Also, if you do string theory, in many cases, if you can superpotential find finite number of solutions. Also, in other kinds of subjects, chemistry and robotics and other things, you find some system with finite number of solutions. That's quite important. Also, it's quite simple because with the algebraic geometry, okay, you can convert this kind of zero-dimensional ideal problem to linear algebra problem. So you can say, if you can do linear algebra in an efficient way, then all these kind of things are solved. Note that this idea could be very high dimensional idea, but don't worry about that. We have algebra geometry. Okay, so let's be careful a little bit right now. You have this kind of F1 to Fk's polynomials in this ring. I call this F. So this F is a simple field. It could be the field of the rational numbers. Okay, because in many cases, the coefficients of the input polynomials are very simple, just with rational numbers. Or at most with an I, or with square root of 2, or we can say it's a finite algebraic extension of the rational number, still a simple field. We have this idea. But then if we try to solve the solution, we don't use the Q because we want to use C. We want the algebraic closure of it to find all the solutions. So here we have to be careful with the notation. When we say Z F bar, we mean actually we go to the algebraic closure to see the number of solutions. Okay. So the first fact is, if you go to this algebraic closure and you solve this equation completely, find that still the solution set is finite. So this one will happen if and only if this R, this ring divided by the idea's quotient ring is a finite dimensional F linear space. You see, this is a very non-trivial result. Why? Because this side, this Z F bar is something like, I'm talking about the points in complex plane. It's a complex high dimensional space, complex. But this R is defined over Q, I, some Q coefficients, and linear space with Q coefficients. So that means there are some correspondence between Q and C. It's very easy to do the computation analytically in this side. Consider the quotient ring R over I, always a rational coefficient, or at the most is I or square root 2 or something. Everything can be done analytically. But this part, if you really go to C, then possibly you have to work with some kind of numerical instability. That's a little bit difficult. Okay, but here you see there's a correspondence. You can use this linear space dimension to predict the number here. Actually, the number of solutions in this C actually equals the dimension R over R as a Q linear space. So that's a very important theorem. Okay. Later I will say that you have to count with multiplicity. For example, if x squared equals 0, actually you have to count it as that's a multiplicity 2 at 0. Okay, 2 roots at the same point, double root. If you use this kind of multiplicity, you can find that the number of solutions in C equals this Q linear space dimension. So here, okay, now the question is, how do we really get this Q linear space dimension? That's easy. We have group basis. Okay, so we try to study this object, this R over R is a quotient ring. Okay, so everything in this idea, I treat it as 0. Then to see what is left. So what is left? That just means, okay, if something is really inside the idea, that means if it's divided by the group basis gets 0. So what is still finite, okay, after this identification R over I? That is something not divided by group basis. Then you can easily say R, okay, the quotient ring R over I equals the span, okay, linear span of all this kind of F. F not divided by any leading term of the group basis, okay. And this one, okay, is of course is a Q linear space. And to determine the dimension, that is possible. So how do you do that? So any kind of polynomial is combined, okay, from monomials. You just need to find all the monomials not divided by any leading term of the group basis. You just exhaust all these kind of monomials. Then you get a linear basis of the quotient ring. Then just check, okay, do I get a finite basis or do I get a countable basis? So countable but infinite, this kind of infinite basis. So in this way, you can easily determine the dimension. I have a package, I will upload it to the Slack. You don't need to do it yourself. If you can get a group basis, for example, this one, you have X, Y, and Z. Of course, you can numerically solve, try to find how many solutions are there. But here, I just tell you that I can do it analytically. So the way I do it is calculate the group basis. Okay, this one looks okay, quite random polynomial, don't say anything. But then, okay, I have in my package, I have a simple tool, try to find all the monomial not divided by any of the leading term in the group basis. I find 8 of them. That means this quotient ring has a basis 8 elements. That means this quotient ring over Q, it has a dimension 8. Immediately, the previous theorem about the 0-dimensional idea tells that over C, this equation system should have 8 solutions. Actually, you can do it numerically with unsolving Mathematica and find that actually there's really 8 solutions. But this kind of thing, numerical result, okay, they are not analytic, some kind of float numbers here. But here, if you do group basis, the group basis computation is over Q. And this kind of quotient ring basis, that's just this kind of division relations as a purely analytical. So I can analytically detect that the number of solutions in C. That is like a magic. But if you are really using singular or not Mathematica, actually you don't need my package, because in singular is something called K-base. So the K-base thing can easily give you the basis for the quotient ring and give you the counting. You don't need to do it by yourself. Okay. So this one is just to tell you the number of solutions. That's not enough. You want to really understand the solutions. So we can further do something like this. I say this quotient ring is a linear span of B1 to BK. So B, there's monomials, and there's a coefficient of 1 monomials, not divided by any of the leading term in the group basis. So, okay, it's very similar. Right now, it's very similar to this kind of group representation theory. Now you have this R over I. This is quotient ring. You know this one is an algebra, because in this R over I, you can add two elements. You can do the multiplication. So it's really an algebra. Then you find actually over this basis, you find a representation given any kind of F, this equivalent class in the quotient ring. You multiply by a basis element Bi. So again, it's in this quotient ring, so it should be linearly spanned over this B1 to Bk. Then you get this kind of matrix Aij. This one is called companion matrix. Note that when I do this kind of multiplication, so this F, I take the Q coefficients. So this B has no coefficient, the coefficient is 1, okay. So I do the computation, multiplication all over Q. And then I get this span here, I divide by group basis, get Aij. Divide by group basis is also computation over Q. So everything is identical. I didn't introduce complex number. I get this this kind of companion matrix with the Q, with all the elements in Q. So it's a simple matrix, analytical matrix. If you have something like I, then you just add some kind of formal definition of I, get the algebra extension. It's also simple, square root 2, square root 2. It's quite simple. Then you get a linear, finite dimensional linear representation of this algebra, or this kind of quotient ring. It's quite easy to say stability because MF plus MG is MF plus G. If you take the multiplication of two matrices, then it's F. It's actually the matrix of the multiplication of the two elements. So it's a abelian representation of it. I also have a small tool to do this in my package. You can download. So for example, again, with the previous example, you have this kind of basis, 8 elements here. I have an arbitrary y square. This is my F polynomial over the group basis. Over this K base is this linear algebra basis. I can get this companion matrix. Okay, this is a companion matrix. It's all simple rational numbers. Now, of course, there should be rational numbers. Okay. Another thing you need to worry about is in different textbooks, okay, they may transpose this companion matrix. So be very careful with it. Either it's defined, okay, this is Ij or it's Gi, and it will be a transpose of it. This is my definition. Okay. Now you have this kind of companion matrix. So what can you do with it? So basically, you can predict the solution. Okay, so here is a theorem. So this Z actually, I really dropped this kind of algebra extension. That means I try to find all the solutions. That is the solution over C here. If there's one solution, okay, and you have some kind of polynomial, then you can say, okay, for this polynomial F, you can calculate the companion matrix, but this Fp must be an eigenvalue of it, okay? On the other side, if you find that this MF has an eigenvalue lambda, then there exists some P in the solution set, and this lambda is Fp, okay? So there's a one-to-one correspondence between the eigenvalues of the companion matrix and the polynomial value on the solution set. So then you have some kind of way to detect the solution set. Okay, you know the solution set will be very complicated. The solution set will be all this kind of numerical values. But here you say, you have this companion matrix, okay, to find the eigenvalue is a quite well-defined linear algebra problem. But if you really want to find the P, okay, in this kind of solution set, it's a nonlinear algebra problem because you really numerically solve this kind of nonlinear polynomial equation. That's something advanced, but then it can be converted to this problem. Find the eigenvalue of it, the linear algebra problem. So this For zero-dimensional ideal, the algebra geometry really convert some nonlinear problem to linear problem. Of course, you have to be more rigorous. You need to consider if you have some kind of multiplicity here. Okay, if you have some double root, then here you also should have the double eigenvalue of it. So with this one very important application is, of course, it's quite obvious. You say if you say I have this function f, this one is a well-defined function, has some physical meaning. I don't want a 1fp. I want to sum over all p here, all the solution p here, get some physical quantity. So that's a situation, for example, in the scattering equation or in the integrability beta-ansatz equation. So here you can just take the sum, okay? But take the sum, you can say each p will be some kind of a numerical value. And then it takes the sum, you get a lot of error in the final result. It seems like not analytic, but you can calculate this MF. This one would be in most cases, that's a rational matrix. Then take the trace. It's quite elegant. The result is automatically analytic and rational. Okay. So I just continue with this example. You have the group basis. You have this kind of linear basis, key basis. You have this kind of companion matrix for y squared. I want to say, okay, I have 8 solutions. So these 8 solutions, they don't look very nice. Okay, there's some kind of real and imaginary parts. My question is, suppose I want a y square evaluated on the 8 solutions and sum over them together. It's very similar to scattering equation or this kind of beta-ansatz equation. Take the sum of it, take the average of it. So what should I get? If you do it numerically, eventually you will also get this number. But if you just take the companion matrix like this and just take the trace, immediately you get a very nice number. And it's a numerical consistent with this kind of sum. Okay. So this way you can really get the analytical results from a high degree and multivariate polynomial system easily. Okay. Or on the other hand, if you know you have some kind of high degree polynomial system, but eventually the physical quantity is quite rational, analytic, then you think that the possibility is from here, because you take the sum or take the average, and then using this theorem, you can say one-to-one correspondence between the solution point and the eigenvalue. So you take the trace, then easily you get a rational result. So here I give you the reference. You can say, sorry, still I have to introduce another technique here. So you may ask me, in cases, for example, if this function is not a polynomial, a rational function, and scattering equation, you have to sum over not just this rational, not just this polynomial function, but some rational function. So this f over g, what can you do here? So the trick here is actually everything is in Hartshorne's textbook. So still this f over g, suppose g is not nowhere 0 on the solution set, then essentially this f over g is called a regular function. Essentially it means it's equivalent to some element. Okay, it's equivalent, say this one is equivalent to some kind of polynomial here. So we consider this kind of here for the long standard sense, if this g is nowhere 0, then there must exist some polynomial h times g plus some elements in I equals 1 here. Okay, but this h is essentially the inverse, okay, the inverse of h on the solution set. So how do you understand it? Because on the solution set, anything from this I is, of course, uniformly 0. Forget about that. This 1 is still 1 here. So it's essentially the h multiplied g is 1 here. So h is essentially the inverse of it. I think it's quite similar to Ben Page's lecture, like why in this z over p, this finite field, a generic number can be inverted. It's the same argument. So this h, of course, it's not inverse, but it's the effective inverse of, sorry, type is g on the solution set. So from this kind of linear algebraic language, you can prove that you have this f over g is a regular function. So if you want to find the companion matrix of f over g, okay, this companion matrix, you can calculate this matrix and that matrix individually, and then take the inverse of the last one. I don't say, okay, this one is the efficient way to get the inverse. There are some other ways to get the inverse better than this. Because the thing is, if you really want to do it antiqually, if you really want to do it antiqually over Q, suppose the matrix is already like 10,000 times 10,000, and suppose a dense matrix takes the inverse, antiqually it's not so easy. You should try to improve this algorithm. You should try to consider, for example, I do the inverse over finite field and do a fitting. Or you should try to say, I try to really solve this kind of here the long-term sense, explicitly find this H instead of to take this dense matrix's inverse. There's a better way to do this. But for our example, this is trivial because let's consider the simple example. I try to sum over, okay, the P in the solution set, x squared over y. This y denominator, I try to inverse this y. Anyway, I just calculate the companion matrix of y, I take the inverse. It's 8 by 8 matrix. It should be inverse quite easily, even it's that dense. Okay. Then I take the multiplication mf dot inverse mg. I take the trace, I get this number. So this number is consistent with the numerical result, but again, it must be analytical and rational. So with this kind of techniques, then you can say there are several papers about the application of a companion matrix or zero-dimensional idea to convert some kind of high degree multivariant polynomial problems to linear algebra problem. So of course, it's a very good paper. Okay, here you can see that's one algebra approach to the scattering equation. Essentially, is this method, the CHY equation, calculate group basis, and then you calculate the companion matrix, take the trace, then you can get this kind of scattering amplitudes analytically. You don't need to really solve the scattering equation because you solve it easier get square roots or get something even worse than square roots if the degree is higher than 4. Okay, but here you can do everything just with the rational numbers or rational functions. So also you can do it with integrability, like some work with my collaborators. You can say you can do the beta ansatz equation. For example, you have some kind of lattice model or spin chain model. You know it's integrable. That means the result should be derived from the algebraic beta ansatz equation. But if you solve beta ansatz equation, you get a lot of square roots or something worse than square roots. But still, as long as you can calculate the global basis, as long as you can get the companion matrix, then you have everything. You can get this kind of partition function. The partition function is also a symmetrical function of the beta roots. Okay, so that's a way to get the analytical results from very high degree complicated multivariant polynomial equation system. I also have to say that here I introduced this kind of companion matrix from global basis because the key step here is I have this basis. The basis is determined by global basis. I have this span, okay, this kind of linear span B, and I have this kind of explicit coefficients because I have group basis. I can do a division, get this kind of coefficients. But I don't say this is the only way to get a companion matrix. If you check other kind of literature, you can find some way. Suppose that it's really difficult to get the group basis. There's also some other way to get the companion matrix without group basis. Okay, so I think the last thing I want to say is for example, sometimes if you really want to get the numerical results, for example, if you want to get okay, this list of numbers, you really want the numbers, and sometimes this unsolved is not very fast, not very stable. So what can you do? So, or sometimes you find the unsolved give you the results, but sometimes you're not quite sure about the multiplicity. So this kind of things. So in this case, what you can do is just follow what I said. Okay. again, use the same kind of language. You have this B, which spans this quotient ring, and then you can evaluate over any point P in the solution set. Note that, okay, this is well defined. Although I have this equivalent class, this is a square bracket here, this one can still be evaluated as P because this F, if you take a different representative of this equivalent class, if you add another polynomial in this I, but this I must vanish on the point P here by the definition. So you can just use this kind of square bracket. So this one, evaluate that. You multiply by that one. But you know that you have this span here. So if you really take this linear span and then evaluate both sides at a particular point P, still the left should equal the right. So you have this equation. But this is a matrix. And you can think of this one with the different values of I, this be a vector. So explicitly you can say, this one is an eigenvector of EIG. But what are the B's? If you go back to the previous example, you can say this K-base example is a linear base example. So this base always contains 1, you can check. It always contains something very simple like this X, Y, Z, the free variables, but it has something high degree, this kind of cubic, quadratic monomials. So you don't need to worry about this kind of high degree ones, just focus on the last form. Now, I only have this kind of EIJ. Suppose I don't know this kind of numerical solution, but then I can try to use linear algebra to find the eigenvector of EIJ. And you may think that the result would be just this B list. This basis list evaluated on the particular point. And this X evaluated on a particular point, that's the first coordinate of the particular point. This Y, of course, evaluated on the same point. The second, this will be the second coordinate of that point. And Z, of course, third coordinate of the point. So here, then you may conclude that if I can, by linear algebra, find the eigenvector of EIJ here, I should be able to find all the coordinates for every point. But the thing is, you have to be very, very careful because the issue here is you need to worry about the normalization because no matter how you do this kind of eigenvector, you have to somehow really fix the normalization. So to fix the normalization, you have to make sure that the last number here, this 1 is a number, it's not a function, it's a 1, evaluated on the point still 1. You have to divide by some constant. That can be easily done. You just divide by the last component of the vector. So this normalization is not a problem. Even more complicated problem is if you find that the AIG has a degeneracy, degenerate eigenvalues, then in each eigenspace, you have some ambiguity how to combine this kind of degenerate states. So in this case, you have to somehow...
Sorry to interrupt. There's a question in the chat. Could you comment about the difference between the companion matrix and numerical algebraic geometry methods?
Yes, that's very different, completely different. The companion matrix is computational algebraic geometry method. It's not a numerical. It's everything actually is analytical. So far, everything is analytical. It's not a numerical. So I didn't mention what a numerical algebraic geometry is, but you can check something. I think I type the software here. You should download this software. It's called Bertini. So Bertini is a numerical algebraic geometry. It's not based on this kind of ring structure or the quotient ring structure, all these kind of things. It's based on some very simple ideas of the deformation, the parameter deformation method of the algebraic system. In some sense, it's originated from Newton's way of this kind of approximation method to find the solution. It's also very, very useful. That's a very good question because in cases, if you really have thousands of equations, and each one is really not linear, some high dimensional ones, then maybe first step to get the global basis calculated is too difficult. But then you should try some kind of numerical algebra geometry method, because that's why it's based on very simple deformation theory methods. Really try to find some kind of typical solution points of it. And then from the typical solution point, try to follow some kind of this kind of flow on the variety, try to find more and more solutions, and eventually try to determine like how many components are there for a solution set. This one, if it's done properly, it's like the primary decomposition. Okay, and then it will also give you this kind of dimension of each component. This one is very similar to the dimension theory in the Hartshorne's textbook. So actually, with the numerical algebra geometry method, we can also do a lot of things. But here, mainly I'm talking about the computational algebra geometry. So everything is analytic. It's not an approximation. It's not numerical. Okay. But you should definitely try to download some software called Bertini and try to run some examples. I can say, okay, maybe it's better because with primary decomposition, it's hard, it's slow, and the result is analytical, but algebraic, you don't see some good geometric picture of it. But with Bertini, okay, at least for simple examples, quickly can finish and tell you that, okay, like it has two components, each one is dimension 1, and each one has some genus. So looks quite user-friendly. Okay. This is also for people doing string theory. If they really have very complicated superpotential, they will try to first use numerical algebra geometry first instead of using whatever computational algebra geometry or companion matrix. But companion matrix definitely is empty. It's not numerical. Okay, let me finish this companion matrix. So I will say if you have some kind of degeneracy of this kind of Aij, then it's bad. You have a degenerate states. You can't say this eigenvalue you calculated must have this form of some kind of basis function evaluated point. So in this case, you have to remove the degeneracy. So how do you remove the degeneracy? That's very easy. So for this kind of analytical computation, you can always do some kind of trial and error. So for this f, if you put one f here, you find that, okay, it's bad, it has some kind of degeneracy. Then you can say, I try some kind of simple linear combination of x and y, z, try linear functions, and maybe also some constant with arbitrary integer coefficients. So for generic integer values, okay, for this x and y, z, and you get this arbitrary, well, this f actually with this arbitrary integer coefficients. Generically, the eigenvalue should not have the degeneracy, and then everything should be can be used. And this kind of trial and error is quite fast because you just use some kind of linear functions with random integer coefficients. After several times, you can find a good f. When you have this good f, when you find that the Aij has no degeneracy, and then you just use the linear algebra to find the eigenvectors and then divide by the last components here, you will get the coordinates of all the solutions. Okay. So this way actually is quite stable, I would say. I don't say this is very fast. It's very stable. It's for some situation very difficult. You're not quite sure about the degeneracy of the solution. You don't know the multiplicity of the solution. It's very good. But I wish that you possibly don't want to really write a program in this algorithm by yourself, because this algorithm is so simple and so easy. So if you download any kind of professional numerical solving program, actually it has some kind of ingredients of this idea inside. Okay, so I think I finished. So finally I finished the lecture 1 and the lecture 2 part. I still have maybe 2 minutes for some questions. Paulo.
Yeah, hi. I was just wondering if you could repeat how you find the companion matrix, because I got a bit lost in that part.
Yes, it's very easy. So first, do you agree that I can get this list, this basis?
Sure.
I just exhaust all the monomials which are not divided by any leading terms in the group of basis. So this one can be easily done.
Sure.
So here, this f is given, f is fixed. Okay. So f multiplied by any of this one. Okay, it's still a polynomial. Okay, it's still a polynomial.
Sure.
But then I can divide by the group of basis. The anything which is divided by the leading term, it's gone, isn't it? F dot bi, I divide it by this group of basis gr here. I just look at the remainder. The remainder must again be a linear combination of it.
Sure.
And the coefficient be numbers. I collect the numbers. So this is a matrix.
Oh, so you just do explicitly. Okay, fine.
Yeah, yeah. I don't think it's very efficient. You can think of some way to improve it, but that's the basic idea. Yes, yeah.
And also one more thing, sorry, when you were, when you said that when you find the eigenvectors that gives you the solution, how that does seem to rely on the fact that you have this linear terms. How are you sure those linear terms are always going to be there?
Because I used this kind, because I used this kind of, degree reverse lexicographic ordering. I always try to pick up one, and if there's no one, I try to pick up linear terms. Okay, but I think when you talk about the rigorous proof, there always should be this kind of linear terms here. Let me think of it. Okay, let me think of it. This kind of thing here. This kind of thing. I think you can check this textbook, Cox Little Osher textbook. So the thing is proved like this. So you first use this kind of degree, this degree ordering, and then you can say that there, if you really get a finite set of this basis, then for each variable x, y, z, there should be some kind of maximum power x to some power y to some power z to some power. Okay, but then I think there should be an argument to say, okay, I think I don't quite remember the details, but I would say that, okay, so if you really don't see this kind of linear term, or if you really don't see this kind of a linear term, that would be a very, very special case. So for example, if you just have one solution, let's consider this kind of a very special case. If you don't have this kind of x, y, z, don't have this kind of high order term, I have one here. It's possible. That means there's only one solution. Okay, but in that case, it seems that this method doesn't work because you don't have this kind of x, y here. But again, then this problem becomes trivial, degenerate, because if you only have one, there's only one solution. Then even you don't need this kind of companion matrix, look at the group of basis. The group basis will be linear. Then from a group basis, this kind of linear generators, you will see this kind of components. So I think it's not necessary they must be x, y, z, the linear term like this. But if you are really missing some of this kind of x or y or z or all of them, actually the situation is getting simpler, not getting even more difficult. But I think I can spend some time try to check out the clear classification of this problem to see if there's missing some x, some y, then how we do it. By my, if I remember it correctly, the situation would be much, much simpler than the case if you have both x, y, and z like that. Okay.
All right, thanks.
Mm-hmm.
Are there any further questions?
Yes, I have a question. For the Galois group and the Sudoku, you were writing the ideals with some rational functions like f of x minus f of y over x minus y.
Yes, so for this Galois theory, I again use this trick. So I have, you can see I have the condition this x1 cannot be the same as x2. So instead of introducing some additional auxiliary variable to claim they cannot be the same, like w dot x1 minus x2 plus 1 equals 0. Okay, if you use this, it's equivalent, but actually you are using more and more variables, not so good. But the thing is, you can use this trick because you just, if this one is 0, actually that means this denominator is well defined and the numerator is 0. So using this condition.
Right,
and,
but it doesn't look like a polynomial.
That is a polynomial. It is a polynomial because there's the same function f with different arguments, and this one must be proportional to a difference. So divide by that is a polynomial. It is a polynomial. It is,
right.
Absolutely. It is. It is. Yes.
Okay.
That's a trick. Yes. You can also use a trick for beta ansatz equations because of beta ansatz, the thing is you have to be very careful. It's not as nice as a scattering equation. You have to consider the case if you have this kind of overlapping beta roots. That's wrong because you can think of the fermions. So, but again, you can use from mathematical viewpoint. Again, you can use this trick. Yeah.
Okay, thanks.
Sorry, I was muted. Yeah, if there are no further questions, let's unmute ourselves and give Yang a round of applause.
Okay. Thanks, everyone.